Writing exponential functions. So an exponential function has the form f of x equals a times b to the x, where a is the starting value and b is the growth or decay factor. And b must be positive, it must be greater than 0, and it cannot equal 1. So here we have a graph. And this looks like an exponential growth function. We have 3 points, but we don't know the y values. So let's say our starting point here on the y-axis, our y-intercept is 0, 200. Then if we wanted to start writing our function, we know the starting value is 200. So we've got f of x equals 200 times something, that will be our growth factor, to the x power. Let's say that point B has coordinates 0.5, 300, and point C has coordinates 2, 1012.5. So I'm going to use the points A and C. And if I look at their outputs, 1012.5 and divide it by 200, I get 5.0625. Now, this isn't the growth factor because the inputs are not 1 unit apart, they are 2 units apart. I'm going from an x value of 0 to an x value of 2. We want to find what the growth factor is by looking at inputs that are 1 unit apart. And so we can take this 5.0625, since that came from values that were 2 units apart, we're going to take the square root or raise it to the 1/2 power. The square root of 5.0625 is 2.25. This is our growth factor. So our function is f of x equals 200 times 2.25 to the x power. Okay, let's look at another graph. Here we have an exponential decay function with 3 points. Let's say point A has coordinates 0, 100, and point B has coordinates 1/4, 50. So my function, f of x equals a times b to the x. We know what a is. Our starting value is 100. So f of x equals 100 times something to the x power. Let's look at our output values, so the ratio of our output values. So we've got 50 over 100, which is 1/2. But that's from 0 to an x value of 1/4. And we want from 0 to 1. So we need to multiply this 1/4 interval by 4. So I'm going to raise my 1/2, which is my ratio I found, to the 4th power. And so 1/2 to the 4th power is 1/16, and that is my decay factor. So my function is f of x equals 100 times 1/16 to the x power. Okay, let's look at a real-life type of problem. A bacteria population starts at 1,000 and doubles every 10 hours. So let's see if we can represent this with an equation. So f of x equals a times b to the x. This is a growth function. And we have a starting value of 1,000. That's our a, so f of x equals 1,000 times something to the x power. And we're told it doubles every 10 hours. So if I have a starting value or y-intercept at 0, 1,000, after 10 hours, so our x value is 10, our output is 2,000. So let's look at the ratio of the outputs. 2,000 over 1,000 is 2, but that's going from 0 to 10. We want from 0 to 1. So we need 1/10 of this, so we will raise the 2 to the 1/10 power. That this whole thing, 2 to the 1/10th power, is our growth factor. So we could write f of x equals 1,000 times 2 to the 1/10th to the x power. Or, using our exponent laws, a power to a power will multiply the exponent, so f of x equals 1,000 times 2 to the x over 10 power. Okay, let's look at another real-life type of problem. You invested $1,000 in a savings account at the end of 5th grade. The account pays 5% annual interest. Okay, so we started off investing $1,000. This is our starting value. So we have 0, 1,000. In 1 year, we'll have an additional 5% interest. So 5% as a decimal is 0.05. I'll multiply that by 1,000 and then add it back to my original $1,000 that we invested. So we have $1,050 at the end of 1 year. So I have a point at 1,050. So my growth factor we'll find by looking at the ratio of our outputs, 1,050 over 1,000, which is 1.05. And we could have also found this as 1 plus r, where r is the interest rate as a decimal. So 5% as a decimal is 0.05. So 1 plus 0.05 is the 1.05 that we found by looking at our outputs. So our function is f of x equals, our starting value was 1,000, and our growth factor is 1.05, and it's raised to the x power. Okay, let's look at another example. We've got the amount of carbon-14 found in an object can be used to date an object, as in tell how old it is. If 1 milligram of carbon-14 was originally found in an object, and the half-life of carbon-14 is 5,730 years, how can we model this with an equation? Okay, so our starting value is 1 milligram. So at time 0, we have 1 milligram. And after 5,730 years, we have half that amount. So we have the point 5,730, 1 half. So if we look at the ratio of the outputs, we have 1 half over 1, which is 1 half. But that's from 0 to 5,730, and we want from 0 to 1. So we will raise the 1 half to the 1 over 5,730th power, and this is our decay factor. So if we look back at our original equation of f of x equals a times b to the x, our starting value is 1, and our growth factor is 1 half to the 1 over 5,730th power, all raised to the x power. Or, multiplying our exponents, we could write f of x equals 1 times 1 half to the x over 5,730th power.